Homework last night, everyone, was worksheet number 2, questions 1 to 8. We got the answers for the first 4 questions up there right now. Have a look at them. Don't worry about copying at the solutions right now. If you had trouble with them, we'll go over them as a group here. Just look at the answers just to make sure you know which ones you need us to go over as a class here. 1 to 4. Okay, have a look at 5 and 6. Again, just the answers. Take a look at the solutions if we need to in a moment. And finally, questions 7 and 8. Any of those 8 questions we need to go over as a group here? Anybody for 6? I knew 6 was coming. Any others? 3? Okay. I got 3. I got 6. Any others? Yep. Any others? 8? 6, 7, and 8 is what we need to go over this morning. So I'm not really surprised at those ones. We can absolutely go over number 3 as well here. All right, number 3. As a 1,500 kilogram car accelerates from 55 to 90 kilometers per hour, what's the impulse? So pretty straightforward in one sense. We know we've got to use impulse because it says so, right? What's the impulse? Okay, that's easy enough. Let's write down some givens, and then we'll figure out what to do with impulse. Here's our mass. This is what? Oh, something jumps out at me here right now. Before I even worry about my givens, I'm going to circle kilometers per hour. How come? Because what? It's wrong? It's not wrong. Kilometers per hour is okay. But I got to convert to meters per second in order to do calculations. So I want to draw attention to that. Circle it in red. Get an ugly highlighter. Get the ugliest colored highlighter you can find. And then every time you come across something like this, kilometers per hour or a negative or something like that, highlight it with the ugliest colored highlighter you can find. You want to draw attention to it, right? Okay. Be ridiculous. You want to draw attention to it somehow in the most ridiculous way so that it does stand out when you go to actually plug the numbers in. Okay, what's this number, 55 kilometers per hour? After we convert it to meters per second, it's going to be called what? V what? The initial, VI. This one is going to be VF. Of course, we do the conversion, but we'll worry about that in a minute. We're looking for impulse. We could call it just the word impulse, or we can say it's delta P, because that's what impulse is, right? Change in momentum. What do you want to do here? Delta P is equal to F times T, or M times delta V, or both. I think it's pretty clear which one we're going to use here, right? We don't know what F is. We don't know what T is. So F times T isn't very useful. Let's try M times delta V. The final velocity works out to be 25 meters per second. 90 divided by 3.6. The initial velocity, I'm not sure what that is. 55 divided by 3.6. 15.278 meters per second. Thank you. Okay, we do the math there. It's going to work out to be, I don't know, 1,400 and something. Is that right? No, sorry, more like 14,000 something. Is it? And the units would be either Newton seconds or kilograms meters per second. Is that okay? All right, number 6. This is the one that I like. Number 6. And I'm not surprised that we struggled with this in a little bit. A 1 kilogram ball traveling toward a soccer player at a velocity of 5 meters per second rebounds off the soccer player's foot. This one jumps out at me. Rebounds. Why? Why is it important to know that it rebounds, that it comes in one way, goes out the other way? Why do I want to draw attention to that with my red circle or my ugly highlighter? It's a change in direction. And when there's a change in direction, there's a change in sign. Something's going to be positive, something's going to be negative. Here's the time of contact. What's the force at the foot applied? This is mass. We'll call this VI. We'll call this VF. But I see that circle to remind me that it's opposite directions. So I got to remember to make one of them negative. Does it matter which one? I don't even remember when I did this question, the answer key that I showed you a minute ago, whether I used toward me as positive or away from me as positive. It doesn't matter though. Right now, I'll define toward me as positive. That means that this is going to be positive 5. This would be negative 8.50 meters per second. If you defined it the other way around, it doesn't matter, as long as you're consistent through the question. You could have defined away from me as positive. This would have been positive 8.5. This would have been negative 5. It doesn't matter. Here's a time, and we want to find a force. Let's say F times T is equal to M times delta V. Delta V is negative 8.5 minus 5. If you defined it the other way around, you would have said 8.5 minus negative 5. I get negative 13.5 there. You would have gotten positive 13.5. That's okay. I think that worked out to be 675, didn't it? Anybody mess up here and call both of these positives? 8.5 and 5, both positives? Okay, that's a really common mistake. Okay, that's a multiple choice question on the test. What you got is going to be there. Okay, but that's why we do this, is practice, right? So that hopefully come test time, you're not going to make that mistake. Remember, circle in red, highlight it with that ugly highlighter, right? Draw attention to it so that it still doesn't completely prevent you from making that mistake, but it reduces the probability of you making that mistake. Okay, 7. So it's a 1.5 kilogram rock falls from the top of a 10-meter high building and strikes the ground. This question's kind of ringing a bell. Deja vu here. Seems like we've had a bunch of questions like this. Until we read the next sentence, it says calculate the impulse experienced by the rock during its fall. Usually at this point, you're asked for the momentum at the end of the fall, not the impulse that it experiences during the fall. Here's my mass. This is my displacement. Typically would be negative. Let's find the impulse. We know that impulse is equal to F times T and is equal to M times delta V. Do we know what F is? What's the force? What causes it to fall? What causes this rock to fall? Gravity. Do we know the force of gravity? No, that's the acceleration of gravity, but minus 9.81 is the acceleration due to gravity. You can find the force by simply multiplying that mass by 9.81. Okay, there's the force of gravity. The time we could find here. Plug it into F times T. Or we could just simply use this part of it and say 1.5 times what's VI? What's VI here? 0. What's VF? How about this? Neg 10 there. What do we get for that VF? Guys are going, making me check my answer sheet again. 14. Final velocity is 14.007, right? Minus the initial, which is 0. Is that right? No, but almost, Lane. Yeah, you're on the right track there. What were you going to say? Yes. The speed is 14. The final velocity is negative 14 because it's going downwards. Multiply those together, we get negative 21.0 Newton seconds, or negative 21 kilograms meters per second. Why is it negative? Well, it's moving downwards. It's speeding up going downwards. A negative impulse comes from either increase in momentum in the negative direction or a decrease in momentum in the positive direction. Either one of those will give you a negative impulse. Jake? That would be fine. No, that's okay. Yeah, absolutely. Now, question 8. When I read this the first time this morning, I thought, wait a second, like it's the same thing, right? Starts off the same way. This one actually wants us to find the force of the ground acting on the rock when it comes to a stop in this much time. Right away, I thought, I know what delta P is. I can find F, and I know what T is. Easy, right? F is equal to delta P over delta T. What's delta P here? Neg 21, is that right? From the last question? Over 0.35. And we get an answer, when we do that, of negative 60. But it's wrong. Although it's very close, it's wrong. What's wrong with it? John? Right. The problem stems from the impulse that we use there. Why is negative 21 wrong? What was the impulse as the rock fell? Negative 21. That's not what we want in question 8. We want the impulse as the rock stopped when it hit the ground. Well, if it gained 21 downward, when it stopped, it lost 21 downward, right? So that would become a positive impulse, which means my force is positive 60 newtons. And that, when we read the answer, should make some sense to us. How do you stop a rock? Apply a downward force or an upward force? Upward. That's why it's a positive force, because it's an upward force. Is that okay, guys? Anybody have any questions about any of those? No? All right. Why don't we have ourselves a little quiz on impulse tomorrow, huh? Want to do that? Let's do it anyway, say. A little quiz on the mathematical part of impulse. All right. Today, we're going to do a little activity in just a few moments. That activity is going to be based on not the mathematical part of impulse, but rather the qualitative part of impulse. One of the qualitative implications of impulse. Yesterday, we talked about 2 different qualitative implications of impulse. The first one, the one we're focusing on today, deals with when we have a predetermined impulse. In other words, the impulse is going to be the same no matter how the object comes to a stop. Told you about my brother when he was your age in the car crash. His car was going to experience the same impulse whether he came to a gradual stop at a stoplight or whether he crashed into that concrete abutment on the bridge. The impulse was going to be the same. His car had a certain mass. His velocity would be 0 minus 100 kilometers per hour. The impulse experienced by the car would be identical. Let's say that impulse was 10 whatever units. Kilonewton second, doesn't matter. Okay, just 10. The impulse was 10. Now let's take a look at the other equation for impulse, m times delta v, but it's also equal to F times delta t. If the time that it takes an object to stop is 2, what's the force got to be that acts on that object? 2 times what equals 10? Lucas? 5. All right, so there's my force. If this force is applied for 2 seconds, it's got to be a 5 Newton force in order to accomplish 10 units of impulse. What happens if the same object comes to a stop in a different way? Well, it experiences the same impulse. Let's say this time, though, the time is 5. It takes longer to stop. What happens to the force? The force has got to be 2 now, right? Notice what we've done here. The object was coming to a stop. It didn't matter how the object came to a stop. Its impulse would be exactly the same, 10. But if it took longer to stop, if the time went up, then the force must have correspondingly gone down. Talked about this a little bit yesterday. The basic idea behind every single thing in the world that cushions an impact, everything that cushions an impact, is this: increase the stopping time, decrease the force. Now, some things also have a second way of protecting you. Say a hockey helmet or a football helmet. There's foam inside, right? Increases the stopping time, decreases the force. But what does a hockey helmet also do? Absorbs it? Yeah. Absorbs it by increasing the stopping time. Yeah. Go ahead. Yeah, so it also spreads it out over a bigger area, right? Okay. I mean, that's something different. What we want to focus on is the first aspect of it, which is increase the stopping time, decrease the force. And that's what you're going to do today. Each group of 2 or 3, you guys can pick your own groups, is going to be given 40 straws, 1 meter of tape, and 1 raw egg. Or 2 or 3 raw eggs if you happen to break them, like one group did this morning. One group broke 3 this morning. Your task is going to be to construct something to put the egg inside of that will allow you to drop the egg from, hopefully, the bridge in the atrium down to the floor without breaking that egg. How are you going to do that? Well, what you want to do is maximize the stopping time of that egg. That's going to minimize the force acting on that egg. Okay. Let's say Fraser has got one apparatus here. Let's say Nick has another apparatus. Their apparatuses are both going to weigh the exact same amount, right? 40 straws, 1 meter of tape, 1 egg, right? They're going to weigh the same amount. When we drop them both, they're both going to be moving the same speed when they hit the ground. 2 seconds later, they're both going to be stopped. They're both going to experience the same impulse. If Fraser can spread out the time more than Nick can, then the force on Fraser's egg will be less. How do we measure that? Well, does the egg break or not? Fraser's egg doesn't break and Nick's egg does break, then Fraser must have spread that time out better. Got it? The only rules here, the egg has to be inside the apparatus. I have to be able to see enough of the egg to determine whether it's broken or not after it's been dropped. And you can't use anything else other than 40 straws, 1 meter of tape, and a raw egg. Got it? That's it. Let's go working on it.